Hello, welcome, croeso, to Explore's new Destination Space show, brought to you in partnership with the UK Space Agency. My name's Kieran and this is Dave, and today we're going to cover 4 topics. Firstly, we're going to talk about how we get things into space, so we're going to do some rocket science, and then we're going to talk about 3 things that we can send to space. We're going to talk about satellites, the James Webb Space Telescope and the ExoMars Mission, and the work going on in the UK currently related to these projects. So we're going to kick off with Dave talking about some rocket science and sending things into space.
Common method for launching rockets is vertically, and I have something here that will show us how one of these rockets works. So first of all, what do we see at the bottom of a rocket when it's taken off? Of course, fire. And we need 3 things to make this a fire, and one of these things is our fuel source. We also need oxygen, which is in our air, and we also need a source of ignition or heat source. So first of all, we're going to use our methylated spirits, which is our fuel, and we're going to mix this with the oxygen in the bottle, and we're going to give it a good shake so we have a mixture of the fuel and the oxygen. So we're just going to drain the rest of the fuel, our spirits, away. So lastly, those are our 2 things. Our third one is our source of ignition. And so before I set it off, we're going to dim down the lights, and then we're going to So by burning the fuel, we create a force, and the force generated on our rocket was an upward force from our fire, and then we had a downward force on the rocket. But obviously, because there was a table in the way, the bottle or our rocket didn't move anywhere. This is a result of Newton's third law, which states for every action there is an equal and opposite reaction. And we're going to demonstrate his third law using a different setup to this, which will show the 2 forces acting on our rocket. So we've seen a vertical rocket being launched and nothing happened. So now we're going to do it horizontally, where we will see Newton's third law in action. By doing this, we're using a smaller bottle where our force will come out the end here. We're using the same fuel and the same source of heat. So, first of all, we have fill the bottle with our methylated spirits, which is our fuel. And we shake and mix the oxygen inside the bottle with the fuel. And then we empty it out. So making sure that the force will come out this end, and then remembering Newton's third law, for every action there is an equal and opposite reaction. The bottle should travel that way. So start our fire in 3, 2, 1. So that was a horizontal launch. This time our rocket moved, unlike our vertical rocket, which stayed where it was because the table was in the way. Our rocket moved this time because there was a force in one direction and an equal and opposite force pushing the bottle, our rocket, in the other direction, which is Newton's third law. So you may think it's strange that we did a horizontal launch, but they actually do launch rockets horizontally, which we'll talk about in a minute. Now we know how rockets are launched, let's look at where they are launched from. Spaceports. Spaceports are like airports, but instead of airplanes, they launch spacecraft. The first spaceport was built in 1950s in Kazakhstan, and in 2015, Tim Peake launched from this spaceport. Okay. The UK is planning on building spaceports to launch vertical rockets and also horizontal. Vertical launches are the preferred method for heavier payloads, whilst horizontal launches will be likely to take passengers and small satellites. There are a few logistics to think about as well. Spaceports need to be far enough away from populated areas so that if something went wrong, such as example they explode, they will not explode over towns or cities where people live. However, people and equipment will need to have easy access to the spaceports, so transport links are important. You will also need a lot of fuel to launch the rockets, so therefore you'll need to make and store fuel on site. As a result, Launch UK is looking at 7 potential spaceports and sites, one of which is in the nearby Snowdonia. The icons on the map will tell you what sort of launches will be taking place from each site. Some have planes and some have rockets. So the 3 at the top are our vertical launches, and the planes will be our horizontal launches. A new engine in development to power these horizontal aircrafts is the Sabre engine. Sabre stands for Synergetic Air-Breathing Rocket Engine, and it can power the aircraft at speeds of 19,000 miles an hour while using less fuel. To see how this engine works, I'll pass over to Kieran.
So this is the setup for our fire tornado demonstration. We've got a bowl of methylated spirits, a fuel we've used already in this show, and we've got a spinning table. So I'm going to light the meths on fire, and then to create a tornado effect, I'm going to use this big metal cylinder here, which I'm going to pop over the top of our meths, make sure they're nice and secure, and then we're going to dim the lights so you can see the full effect of the fire tornado. So when air gets hot, it rises. Now obviously the air at the bottom of the bowl is getting a lot hotter because of the fire, which means there's now less air at the bottom of the bowl. Now when I spin the table round in a moment, air is going to be dragged through the holes in this cylinder and it has to go somewhere. It's got a nice gap now near the bottom of the bowl where there's less air, so that's where a lot of the air will go. So if I spin the table around, you can see that the fire gets bigger and it's also in a tornado shape. Now the reason the fire is getting bigger, if you think back to Dave's fire triangle from before, the 3 things we need for a fire are fuel, heat and oxygen. To make a fire bigger, you can add more fuel to it, but you can also add more oxygen, which is what we're doing here. And that is the same principle that the Sabre engine will use to create a larger reaction inside.
One thing we can launch from these spaceports are satellites. The UK is the world leader in satellite design and construction. And with the new spaceports, we can look forward to being a world leader in launching them too. Satellites are anything that we intentionally placed into orbit. Sometimes we call them artificial satellites to distinguish them from natural objects orbiting the Earth, such as the Moon. There are different uses for the artificial satellites orbiting Earth. Some are used for GPS, some are for tracking wildlife, some can be used for communications such as mobile phones and the internet, while others can be used to take pictures and images so we can map out the Earth, and this is sometimes used by Google Maps. As well as satellites, there are other things that we do send into space, and Kieran will now talk about this.
So Dave has just talked about how we can launch satellites into space to help us map the Earth, but we can also launch telescopes into space to help us map space itself. Telescopes located in space are known as space telescopes, and the most famous example of a space telescope is probably the Hubble Space Telescope that was launched in the early 1990s. The Hubble Space Telescope has been responsible for some of the most iconic images of the cosmos ever taken. But next year, on Halloween, the successor to the Hubble Space Telescope will launch. The James Webb Space Telescope is a collaboration between NASA, the UK Space Agency and the European Space Agency, and it's named after James Webb, the second ever administrator of NASA. The James Webb Space Telescope will allow us to see further into space than we've ever seen before, and hopefully help us answer some of humanity's greatest questions, such as, are we alone in the universe? There are two main differences between the James Webb Space Telescope and the Hubble Space Telescope. The first difference is that the Hubble Space Telescope is only 500 miles from the Earth, whereas the James Webb Space Telescope will sit much further away, about 1 million miles from Earth. This means that astronauts will not be able to visit the James Webb Space Telescope to carry out repairs, as they have done with the Hubble Space Telescope. But the second main difference is probably the key difference, and that is how the telescopes see space. Now, the Hubble Space Telescope uses what we call visible light to see space, whereas the James Webb Space Telescope will use something called infrared light. Now, you might be thinking, isn't all light visible? Light is just us seeing things, but actually there are different sorts of light that we can't see. The light that we see we call visible light, but it represents only a really small section of the spectrum of light. Behind me here I have a picture of the electromagnetic spectrum, of which visible light is only one small part. This spectrum shows the entire range of electromagnetic radiation, from radio waves through visible light all the way through to gamma rays. Electromagnetic radiation varies in its frequency and its wavelength. With visible light, which is found in the middle of the spectrum, longer wavelengths we see as red, whereas shorter wavelengths we see as blue. But beyond blue and beyond red, we have other wavelengths that we can't see. Beyond blue, we call the light ultraviolet because it's past the violet end of the visible spectrum, and beyond red, we call it infrared, and it is infrared light that the James Webb Space Telescope will mainly view. So why will infrared light allow us to see further into space than visible light? Well, there are actually two reasons. The first is because lots of light from the most distant regions of space has been red shifted, and the second reason is because infrared light allows us to see through objects through which visible light might not be able to pass. So firstly, I will talk about red shift. I mentioned before that longer wavelengths of light appear more red to our eyes, and there are some wavelengths that are so long that we can't actually detect them with our own eyes. Light that's been travelling through space can be red shifted. This is because everything in space is actually moving away from us because the universe is expanding. This means light from distant objects has had to travel through expanding space before it reaches the Earth, so the wavelength of light has been stretched out, and we call this redshift. To help me demonstrate what I mean, me and Dave are going to use a slinky to demonstrate redshift. To demonstrate the different wavelengths of light and how they change as light moves through space, I'm going to use a slinky, and I'm going to ask Dave to help me demonstrate this. Dave and I are going to move the slinky in a wave shape, similar to wavelengths of light. We can shake the slinky slower, like orange and red light, and we can shake it more quickly, like green, blue and violet light. As we move apart, the wavelength of light gets stretched out, and this is what's happening when light is red shifted. Wavelengths of light grow longer as they move through expanding space. So we saw then how light that's travelling through expanding space has its wavelength stretched. So viewing the infrared spectrum will help us view these objects. Now the second reason that infrared light helps us see more of space, as I mentioned, is because we can see infrared light through some objects which might otherwise block out visible light. Things such as huge clouds of dust and gas can block out visible light from stars and planets, but infrared light can often shine through these objects, allowing us to see what lies behind. To demonstrate this, me and Dave are going to use the infrared camera in the exhibition space at Explore. So we have Dave here, who's going to be quite literally the star of our show. So at the moment we can see Dave nice and easily using visible light, but all of a sudden our star is passing behind a huge cloud of dust and gas, which in this case is a bin bag. This is blocking out the visible light so we can no longer see Dave. But if we pan round to the infrared camera in our exhibition space, we can now see Dave through the bin bag due to the infrared radiation being given off by Dave. And to prove that we didn't cut anything there, we can pan back and see Dave with his bin bag cloud hat. So the things that are giving off heat give off lots of infrared radiation, things such as Dave, stars and planets. You might have seen things that are glowing red hot or perhaps even white hot, and this is because things that are hot do give off some visible light, but most of the radiation given off is actually in the infrared part of the spectrum. As infrared light can more easily travel through objects such as clouds of dust and gas, viewing space in the infrared spectrum allows us to see through these objects. So we've talked about viewing things in space, but we're going to end our show by talking about visiting space itself, and more specifically about visiting other planets. So now I'm going to talk about the ExoMars mission that will be launching in September 2022. So there are 8 planets in our solar system. There's the rocky planets, which is ourselves, Mercury, Venus and Mars, and the 4 gas planets of Jupiter, Saturn, Uranus and Neptune. But we want to investigate life in the universe and if there is any life out there. And that means some of these planets are out of the question. Obviously the gas giants won't be able to support life because there are no solid surfaces. And if there are solid surfaces deep down in these planets near the core, the pressure will probably be too much to support any sort of life. For Mercury, the temperature swings on Mercury are far too great to support life as we know it, with the sunny side of Mercury reaching up to 400 degrees Celsius and the shaded side reaching minus 200 degrees. And similarly, on Venus, the temperatures can exceed 450 degrees Celsius. And that's before we get to the acid rain, poisonous atmosphere and thick clouds. So if we're looking for life in the universe, Mars might be our best bet. So I mentioned before how our mission to Mars is launching in September 2022, and this is because this is a date when the Earth and Mars are closer together. Now the Earth and Mars aren't always the same distance apart. Sometimes they're only 30 million miles away, whereas other times they are over 90 million miles apart. We pick launch dates when the Earth and Mars are closer together to save on fuel and to cut down the mission time. Now when we're talking about such vast distances, it's helpful to have some frame of reference. So if we think about the closest natural object in space to the Earth, which is the Moon, that is only 250,000 miles away. Whereas even a close distance between Earth and Mars, say 30 million miles, is a lot further than that. And you can see the difference on the screen behind me. So now I've talked about getting to Mars and the distances between the Earth and Mars, I'm going to talk about the mission itself. Now the main objective for the upcoming ExoMars mission is to look for signs of past life on Mars. And we think Mars is a really good candidate for finding signs of past life because millions or perhaps even billions of years ago, we think Mars was covered with water. and all life as we know it needs water to evolve. The reason we think Mars had water on its surface is because of its red colour. Now, it's a common misconception that Mars's red colour is because it's hot. It's actually very cold on Mars, and the red colour comes from a layer of rust covering the Martian surface. If you've ever left a bike or a scooter out in the rain, you will know that they can go rusty. For rust to form, we need three things. We need a metal, we need oxygen, and crucially, as far as Mars is concerned, we need water. So the presence of rust on the surface of Mars indicates that it was once covered with water. In fact, in September 2020, scientists found underground lakes on Mars. These lakes are really salty, but they could perhaps have life in them that has evolved slightly differently from life on Earth. Now, the ExoMars mission is a very special mission because it'll be the first to drill down below the Martian surface to look for signs of life. The reason it has to drill down to the surface, under the surface of Mars, is because, as I mentioned, Mars's surface is actually really cold, the average temperature being a rather chilly minus 63 degrees Celsius. This is probably too cold for any life to evolve or survive, so by drilling down below the surface, where it's more insulated, there might be some signs of life. So why might a temperature of minus 63 degrees be too cold for life to evolve? I'm now going to do a demonstration with some glow sticks to demonstrate why this is the case. The low Martian temperatures are one of the main barriers for life on the red planet. This is because chemical reactions occur more slowly at lower temperatures, and chemical reactions are absolutely vital for life. In fact, life really is one long series of chemical reactions. Thousands of chemical reactions occur every second in our bodies and in the bodies of all living organisms, when we move, when we grow, when we eat, and even when we think. To demonstrate how temperature affects the rate of chemical reactions, I'm going to use a glow stick. Now, glow sticks can be a source of light because of the chemicals inside them. Generally, we think of light sources as coming from electricity or from heat, but we can also use chemicals as a light source, and this is called chemoluminescence. This is actually how some biological organisms that give off light are able to do so. Things like fireflies, anglerfish, some glowing fungi use chemicals inside their bodies to give off light, and when it happens inside living organisms, it's known as bioluminescence. So I'm going to crack the glow stick, and that characteristic cracking sound you hear when you break a glow stick like this is the sound of a vial inside breaking, which releases some chemicals. They can then mix with the other chemicals inside the glow stick, and a chemical reaction occurs which gives off light. And give it a shake to mix the chemicals all the way through the glow stick, and we are going to dim the lights to show the effect of this. So I'm going to pop the glow stick inside some hot water. This will increase the temperature of the chemicals inside, which will speed up the rate of chemical reaction, which means more light will be given off, so the glow stick will appear brighter. So if I take the glow stick out of the water now, you can see the end that was inside the hot water is now brighter, and now I'm going to dip it into some cold water, and the opposite should happen. So as I pop the glow stick in the cold water, the temperature inside is lowered, which means the rate of chemical reaction is slowed down, less light is given off, and the glow stick appears to be more dim, as you can see there. The reason that the ExoMars rover is going to drill down into the surface of Mars is because of the insulating effect this can have below the surface. Hopefully the temperature below the surface is warmer than that at the surface, which means we're more likely to find life or signs of life below the surface of Mars. We've seen with that experiment why it's important for the rover to drill below the surface of Mars. The rover will be able to analyse the samples it takes from below the surface using an onboard lab to look for signs of life. The rover itself is called the Rosalind Franklin rover, named after British scientist Rosalind Franklin. Now, Rosalind Franklin isn't as famous as she should be. She worked mainly in the 1950s and was influential in discovering the structure of DNA. Now, if you ask most people who discovered the structure of DNA, they will say Watson and Crick because they got all the credit. Now, in the 1950s, there was a big push to discover the structure of DNA in order for us to learn how it worked exactly. There were several laboratories throughout the world trying to uncover this secret. Rosalind Franklin worked in one, and Watson and Crick worked in another. Rosalind Franklin used a technique that she developed called X-ray crystallography to take X-ray pictures of cells to try and uncover the structure of DNA. Even one of these pictures could take over 100 hours to develop. Without her consent or knowledge, a member of her laboratory took one of her pictures, which is known as photograph 51, gave it to Watson and Crick, who used it to help them confirm their suspicions of the structure of DNA based on their own work. Watson and Crick's work was published using Franklin's photograph before Franklin's work, and they got all the credit. Naming this rover after her is just one way in which scientists are striving to honour the legacy of Rosalind Franklin. Thank you for watching our presentation today. We hope you enjoyed it. If you'd like to find out any more about the Destination Space project, email projects@explorescience.co.uk or visit one of our social media links. Bye.
Goodbye.